Hello and welcome back to Counting Rocks, an introduction to combinatorics at CSU. Today we're going to be talking about planar graphs. A graph is planar if it can be drawn in the plane with no two edges crossing. Now, this graph has two edges crossing as we drew it here, but it is actually planar because remember, a graph is only the data of which vertices are connected to which other vertices. Here's the complete graph K4, and we can draw it in a different way, where all four vertices are spread out like this with one in the middle, and all four vertices are all connected to each other by edges. So this is a complete K4 as well, and it's just this graph drawn in a different way. To get from here to here visually, you can think of taking this point and dragging it into the center of that triangle and then rearranging the triangle a little bit, and you'll get that diagram. So K4 is planar. Even though it's not planar in every way of drawing it, if there exists some way of drawing it in the plane so that no two edges cross, then it's planar. We write f for the number of faces of a planar graph, and in this case it's 4, because we have 1, 2, 3, 4 faces. We count the outside face as well. E is the number of edges, which is 6, and v is the number of vertices, which is 4. Now, it's not clear that the number of faces is well defined. Number of vertices and number of edges is certainly a property of the graph. But for number of faces, doesn't it depend on how you embed the graph in the plane? What if we move these vertices in some other way that's also a planar graph? Why is the number of faces well defined? Well, here's where Euler's formula comes in. In any planar graph, v minus e plus f equals 2. This is Euler's formula for planar graphs. And that means that if you have a graph and you know the number of vertices and you know the number of edges, then the number of faces is actually determined uniquely. So Euler's formula comes in handy here. No, we count the outside face again, so number of faces includes the region of the plane outside the entire graph. Here's an example of a non-planar graph. So how do you determine when a graph is planar and when it is not? B33 is a non-planar graph. No matter how you move the vertices around, you can't uncross the edges. You're also allowed to make the edges non-straight. For instance, I can take this edge and draw it this way, looping around the other vertices, but even if we do all that, even if we allow every possible bending and twisting and moving of the vertices, we will never be able to embed at B33 in the plane without two edges crossing over each other. Let's look at a proof of this using Euler's formula. Let's assume for contradiction that it is a planar graph with f faces. Then let's use Euler's formula to figure out how many faces there are. There are 6 vertices in this graph and 9 edges because 3 times 3 edges in a complete bipartite graph here. So v minus e plus f is 6 minus 9 plus f, which is a negative 3 plus f. And that equals 2. So solving for f, we find f equals 5. So any way of embedding this in the plane, if we're able to do it, assuming for contradiction that we're able to do it, we'll have 5 faces. Now what goes wrong with this? There have to be at least 4 edges per face. The reason is any cycle in a bipartite graph has to have at least 4 edges. So here's a minimum cycle, right? 1, 2, 3, 4. If you go just from this side to that side, you can't go directly back to form a cycle because we don't have multiple edges in B33. And you can't have a cycle of length 3 because you'll be on the other side of the bipartite graph, which doesn't have edges between it. If you start and end in the same side, we can't complete that cycle without going over to a 4th vertex and then completing it back up. So every face must have at least 4 edges because every face will be surrounded by a cycle of edges, and the cycles all have length at least 4 in this graph. So that means 4 times f is twice the number of edges, because think about it, each edge borders 2 faces, one on each side in a planar graph embedding, and so twice the number of edges is at least 4 times the number of faces, because there might be more than 4 edges on some face. Maybe some face has 6 edges, say. But 4f is a lower bound on the value of tracing around each face and counting all the edges, which is twice the number of edges. And so 4f is less than or equal to 2e. We can divide both sides by 2 to get 2f is less than or equal to e. But e equals 9 here, right? There's 9 edges in this complete bipartite graph. And 2f is 2 times 5, which is 10. But 9 is less than 10, so we don't have 10 is less than or equal to 9, so that's a contradiction. So actually, B33 cannot be embedded in the plane. Here's another non-planar graph, K5, and in the textbook we go through the proof as to why K5 cannot be embedded in the plane. Very similar proof, and you can see if you can work it out on your own. So it turns out that B33 and K5 are sort of the 2 most basic non-planar graphs from which every other non-planar graph can be constructed. So let's look at graph minors in order to see how we can do this. A graph minor is formed by contraction and deletion operators. So first we need to understand edge contraction. Edge contraction is formed by taking an edge in your graph and contracting it, meaning shrinking it down to a point. Or technically, we can think of deleting this edge and taking its two endpoints and merging them to be the same endpoint, but then carrying all the other edges along with them. So we're identifying V1 and V2 here, say, as a single vertex, and making all the other edges remain the same under that identification. So here we've contracted this edge, this yellow edge, down to a point. And then a deletion is any deletion of an edge, so I could have actually just erased this edge, that would have formed a minor. Or you can delete an isolated vertex. And what that also means is you can take a vertex like this one and delete the vertex and all edges connected to it. That's called a vertex deletion. The reason we can do vertex deletions is that we can think of deleting this edge and then deleting this edge, and then we'll have an isolated vertex here that we can delete from the whole picture. So for instance, you can get this graph as a minor as well by doing this edge contraction and then these two edge deletions and this vertex deletion, and we're left with a very small graph down here. The study of graph minors is a very interesting problem in graph theory, especially reconstructing graphs from minors. This is a famous reconstruction problem in mathematics. A graph minor, then, is just any graph that's formed by a sequence of deletions and contractions. So what do graph minors have to do with planar graphs? Well, first of all, notice that contracting an edge, if it is planar, remains planar wherever we draw it. So contracting an edge won't force you to have two edges crossing. And also, deleting edges or deleting vertices also certainly won't make two edges cross. So contraction and deletion is something that preserves planarity. If you start with a planar graph, then every minor is going to be planar. And so here's the big theorem. Kuratowski's theorem says that a graph is planar if and only if it has no minor equal to B33 or K5. So this is very powerful because we've just said that every minor of a planar graph is planar. So then that means that if the graph has a minor that you know is not planar, like B33 or K5, then the whole graph isn't planar. So certainly one direction of this if and only if is clear because we showed that B33 and K5 are not planar. So if you have a B33 or K5 minor, then you're not planar. But why is it if and only if? That's a very complicated question, and the proof of Kuratowski's theorem is not easy. So we're just going to use it in this class. Let's use it to prove that the Peterson graph is not planar. This is a very famous graph called the Peterson graph. It's a nice graph where you have 5 vertices around in a pentagon, and then 5 vertices inside forming a star, and then you connect the corresponding vertices of the star to the pentagon. Well, this has K5 as a minor, and the reason is you can contract these little connector edges, all 5 of them, do 5 edge contractions, and that forms a minor that's exactly the complete graph K5 on 5 vertices. And so now you try. Is this graph planar? Why or why not? Can you find a B33 or a K5 as a minor, for instance? And that's all for today, and I'll see you next time.